Hello, in this presentation, I reproduce the metadata assisted cascading ensemble or MACE for Open IoT data. I then extend the approach using class specific model competence, hierarchy construction, and filtering. The MACE framework first evaluates 5 standalone classifiers operating on time series, statistical, and metadata representation. In the first cross-validation stage, top K accuracy is used to select the classifiers and determine their ordering in the cascade. Once this hierarchy is fixed, a second 5-fold cross-validation stage tunes the survival of the fittest filtering parameter. During prediction, the classifiers are then applied sequentially, with each stage filtering and the candidate classes passed to the next classifier. The key idea behind MACE is not to freeze the prediction at the highest scoring class. For each sample, the classifier ranks all 21 classes. As these examples show, a true class missed at top 1 may still appear within top 2 or top 3. Top K accuracy therefore measures the proportion of validation samples whose true class occurs within the top K predictions. Repeating this for 5 classifiers and 21 values of K creates the 5 by 21 matrix used in CV1 to construct the global hierarchy. CV2 then tunes the SOF filtering parameter. For part 1, the reproduced standalone classifier performance was comparable with the paper. However, the hierarchy obtained from my cross-validation was different. 1 NNED followed by DDL NLP and random forest. The SOF parameter was tuned using 5-fold cross-validation over 0 to 1 in steps of 0.1 with 0 selected as optimal. The final reproduced MACE achieved 86.19% accuracy and 77.53% macro F1 compared to the paper's reported 88.2% accuracy and 79.4% F1 on ThinkSpeak. In part 2, I extend MACE from global optimization to class-specific optimization. The 21 class problem is converted into 21 versus rest problems, giving 105 classifier evaluations. Instead of global top K accuracy, class-wise F1 is used to construct a 5 by 21 by 21 competence tensor and an independent hierarchy for each class. I also introduce patience-based hierarchy swapping, optimize the SOF parameters separately for each class, use class weighting to address imbalance, and perform additional hyperparameter tuning where applicable. First, I compared the two patience settings within part 2. Patience 2 produced improvements for several classes including class 15, 16, 10 and 6, although some classes declined and many remained unchanged. At the macro level, Patience 2 also improved over Patience 1, increasing macro F1 from 72.63 to 74.69%. I therefore selected Patience 2 for the final comparison. Comparing the selected part 2 solution with part 1, however, shows that the improvement is not uniform. 13 of the 21 classes have lower F1 and these classes represent about 65% of the test set samples. Importantly, this does not mean that 65% of individual prediction became worse. It describes the support of classes whose aggregate F1 declined. The imbalance analysis provided an explanation. Several of the poorer performing classes have very small training support and severe 1 versus rest imbalance. Consequently, part 1 still gives the stronger overall macro performance. In conclusion, the class-aware extension provided greater flexibility, but increased complexity did not automatically improve overall performance. The analysis suggests that severe class imbalance was a major limitation and class weighting alone was insufficient for several minority classes. Future work could therefore investigate data-level balancing methods such as SMOT, temporal train test splitting to better preserve the IoT data characteristics, broader patience experiments, and more advanced classifiers with further hyperparameter optimization. Overall, the study demonstrates both the potential and the limitation of extending MACE towards class-specific optimization.